All right. Can you hear me? Good? Yay! All right. Today I'm going to talk about multitasking on Cortex M, or more especially Cortex M0 class MCUs. I gave a talk last year about the Chromium EC, which is the firmware that we run on, Chromebooks and a bunch of Google devices. Disclaimer: I don't work for Google. I work for Edis Research or National Instruments. And I'm an embedded software engineer at National Instruments. I do all kinds of embedded things. Firmware is one of them. And last year I was speaking about how you could use Chromium EC for your own projects. And this year I'm here and we just finished our first product that will release soonish that actually uses Chromium EC as firmware for temperature control, for fan control. And we're probably going to use it for future ones. Other stuff I do, I'm a co-maintainer for the FPGA Manager framework, and I do random drive-by contributions to stuff we use or stuff that I'm interested in. I'll jump directly to the meat. So the microcontroller that I picked for my presentation is a Cortex M0. And it's ARM v6, which is kind of oldish already, but it's also very nice because it's very simple. And it's a good example to walk through multitasking and how we get there by using all the features that this core gives us. So the registers are not a lot. We get 16 registers. The blue ones are low registers. They're a bit special. The Cortex M0 runs only thumb mode. So there's limited size in the instructions. So some instructions will just let us access the lower ones, which are the blue ones. We'll see that later in action where we actually run into that issue. R13 is our stack pointer, which could also be called SP. So you can use R13 or SP both in your assembler. There's a program status register that, depending on the mode you're in and depending which name you use when you try to read it, you'll get different things. We'll see all that later when we look at the registers individually. There's a priority mask register, which we'll also talk about later, and a control register, which is very simple for the Cortex M0 specifically. So let's talk a bit about the stack pointer. That's the thing we're going to play around the most with in the code we're looking at. So basically, you use a stack if you have a bunch of stuff that doesn't fit anymore into your register. So you just push it on the stack, which is RAM. And then later on, you pop it off again. So in this example here, I completely made up the values, but you have a stack pointer that points to an address. We have a register R7 that we want to store. So we do a push R7, which puts it on the stack, which decreases our stack pointer by exactly 4 bytes. On the Cortex M0, our stack is always word aligned, so always 4 byte aligned. The lowest 2 bits can therefore be 0 because we know they'll be aligned. And the stack is full descending. So as we see, the stack decreases whenever we push something, and the stack pointer value decreases whenever we push something, and it increases when we pop something. So we have a link register and a program counter register also. The link register is basically if you call a subroutine, then you put in the value from the next program counter value that you run when you get back from there. So the link register is also a bit special. We're going to talk about it later when we look at the thumb state, that the different states that our processor can be in. And the bit 0 is the bit 0 in the link register indicates that we return to thumb state when we use the link register to return. Some instructions will need that to be set, but we'll also see that later when we actually make use of all these things that I outline here. The program counter, when you read that, give you the current instruction plus 4 because it's a pipeline processor, and the program counter bit 0 should be 0, but some instructions like BX and BLX require them to be set because we want to stay in thumb mode. The combined status register, depending on which mode you're in and how you read it, you'll get different values to read. First one is the application status register, which contains your ALU things like not, zero, carry, and overflow. For example, if the instruction before created an overflow, or if you did a compare and it's not, or if you compare and there's a zero, or you do an addition and there would be a carry, all those would get set in that part. You see that the rest is reserved. There's an IPSR, which is your interact program status register, which the lower 6 bits will give you the exception number that cost you to get there, so it's pretty handy if you need to figure out what happened. For example, say you have a default handler, you jump there and you want to know what caused the exception that got you into the default handler, you could look at that and it would tell you. The EPSR is the exception program status registers, not so important for what we're going to do, just for completeness it's here. All right, calling convention. It's assume you usually program C, then your compiler would use certain registers for certain things when calling a function, for example. So R0 through R3 are usually used to pass arguments. R0 and R1, if the result, are also the result register. So depending on the size of your result, it will spill over into R1 and so on if your return value is bigger. There are R4 and R8, also R9 is a bit special, but we can ignore that for what we're doing here. So R4 through R11 are callee safe registers, which means your function needs to restore them back to the value they were before you jumped into the function. R12 through R15 are the special registers, which we saw already before, so it's like stack pointer and so on. Yeah, so priority mask is the register that we're going to use to disable exceptions that are programmable. So you write a 1, then no interrupts happen. You write a 0, it's not masked, all right? Am I going too fast? Can people still follow? It's a lot of things, good. There's a control register, something we're going to play with a lot. What the control register does on the Cortex M0. Bit 0 is reserved, so that's for upwards compatibility with other Cortex M class CPUs. We don't have privileged mode or unprivileged mode on the Cortex M0, but on M3 that bit would be your privilege. The control, the bit 1 in there, lets you select which one is your current stack pointer. So as we saw before when I showed the registers, there's a PSP and a MSP. The PSP is the process stack pointer, while the MSP is your main stack pointer. Writing that bit while you're in thread mode, which we'll see in a second, will switch between the two. And that's really cool for implementing task switching, which we'll see also later. All right, this is a thumb state, basically what it's called. So it shows you the states you could be in. There's the handler mode, which is basically where you'd run all your OS things, and there's thread mode, which is where all your normal task code runs. And you get from thread mode to handler mode by taking an exception. And then depending on whether your control bit is set on return, So there's two modes, and depending on whether the control bit 1 is set, depends where you're going to stack your registers, which we'll see on the stacking slide that follows. And yeah, but first, okay, what's an exception? In short, it's basically an event that changes the program flow. You jump to the exception handler, and it suspends the current code that runs, and then you run the exception handler, and then you assume where you left off. And some exceptions on the Cortex M0 have fixed priorities, like reset, non-maskable interrupt, and hard fold. They're negative priorities. Some exceptions have programmable priority, so that lets you arrange things in the system as you need. So you could prioritize different interrupts differently programmatically. 0 is the highest priority. Of course, there's the negative ones that have higher ones, but you can't mask those. The prime mask one, as we said before, can be used to mask interrupts, and interrupts that can't immediately get handled can be pending. All right. The Cortex M0 has vectored interrupts, which means you set up a vector table, table of interrupt vectors, which means a table of pointers to where you want to jump for certain exceptions. That table contains the addresses, and the processor will automatically jump to the handler if one is set up, and usually it's a good idea if you don't have a handler set up to use a default handler for the other ones, and then have something like an infinite loop to trap it there so it's easy when you debug to figure out what happened. All right, so what happens on exception entry stacking with the main stack pointer? There's two ways, as I said, depending on the control register, how you could stack your registers when you take an exception. The first one is the simple one when you're not using the process stack pointer, and when you're not using the process stack pointer but just the main stack pointer. In that case, you run here in thread mode, then you take your exception. Automatically the processor will push the exception context, which is a subset of all the registers, onto the current stack. The registers in the exception context are R0 through R3, R12, link register, program counter, and the current status register. And the stacking always happens on your current stack, whatever is selected when you're in thread mode, all right? And that makes nesting possible, which we'll see later. And the unstacking happens based on the link register values. So when you enter the exception based on what mode you're in and what setup you had for your stack pointer, there will be a different value in link register, which we'll see also soon. The other case, which is the slightly more complex case, is when you actually use the process stack pointer, which is what you're going to do when you actually do multitasking, all right? So there's a main stack pointer that's going to be used when you're in handler mode, because handler mode always uses the main stack pointer. In thread mode, you'll select which one gets used. So you're here in thread mode, you get your exception, you're using process stack pointer, remember, because that's the point of this example. So your stuff gets pushed onto your process stack pointer, and then you go to handler mode, which automatically switches your stack pointer to use the main stack. Then you do whatever you do in your handler, and then the unstacking, because of the link register value, will happen again from your process stack pointer. And this is going to be basically how we're going to do multitasking later, but more on that later. Okay, exceptions. Tail chaining, so there's a bunch of neat features that allow the processor to be more efficient when handling exceptions. So the first one is here that if you get an exception and another one happens, that has a lower priority while the first handler runs, you'll not unstack, but you'll directly go to the handler B and reuse that stacking. So you save this entire part where you would have to first push stuff, pop stuff, push stuff. So instead you use the first exception context for the second one too. Then there's the late arrival case where basically you take an exception A and then a higher priority exception B arrives before the handler for A would run, and then you could just directly run the handler for B and then the handler for A. And then there's the complex case of nested ones, where you again take your exception, then your handler starts running, you take another one, you go up, and then stacking happens twice. So let's say here you had the process stack pointer, you stack on the process stack pointer here you're in handler mode already, so you're going to use the main stack pointer, you stack another exception context, and then you go back. All right, if that wasn't complex enough, here's another picture that I drew. I know it's beautiful. Basically, again, thread mode, handler mode, depending on your stack pointers, there's all these different ways you could go. I'm not going to go into details. One thing to note, however, is that on taking the exception, the value that gets put into the link register will determine our path back. So it will determine basically whether we unstack from the process stack pointer or the main stack pointer. So for the nested case, for example, we'd go take the exception, we use the process stack pointer, now we're in handler mode already. If we get another exception, now we stack on the main stack pointer, and then we could go in several times till stacking, and then the unstacking would happen based on the link register value, which would get put in the link register based on how we got there. So there's always a way out. All right, so now we talked about all stacks, exceptions, stacks. So now we're going to look at how do we get from the reset to actually running C code, right? Because that's what we want to do. On reset, the execution basically jumps to a reset vector. We do a bunch of stuff before we can run normal C. What we're going to do is make sure we're in the right state. So we want to set our main stack pointer, and we want to make sure that we're in the right state, thumb and privileged, or not. In the Cortex M0 case, we don't care about the privilege. We want to initialize our BSS section to 0. We want to copy exception vectors to SRAM, which is a bit specific to each core in the Cortex M0 that I was using, which is an STM. You'd have to copy them over to SRAM to speed up the fetches. All right, and then we copy the initialized data section, so that would be global variables that have a value. We copy that to SRAM. We set our initial stack pointer, and finally we jump to main. So how does that look in the Chromium EC code? Well, after reset, we make sure that our control register is 0. Remember, control register 0 means we're non-privileged and we're using the main stack pointer. Then we wait for that to actually happen, so the ISP will just wait for things to go all the way through. Sorry. And then, we have a bunch of loops to first zero the BSS section. Then we have a vtable loop where we copy over the exception vectors to RAM. Then we tell our microcontroller to please use exceptions now from the new copied vector table. Then we have a data loop which will go and copy the initialized data from flash to RAM, and then we can finally jump to main. So not so complex, right? Everyone still on board? Did I lose everyone? No? Good. Sorry? Oh, all right. Sorry. All right, so multitasking, again, that's what we want to do, right? So we're trying to context switch. So the idea is we have multiple tasks. We want to decouple them as much as possible from each other. And we want them to be able to run task A, then OS, then task B, then task C, whatever order, but the tasks should not have to know about each other unless they actually do want to interact, all right? So that makes writing code really nice, because as the programmer writing code for that task, I don't have to be concerned with what other people do, because while I run, it looks to me as if I own the whole thing. And there's cooperative approaches too, where the tasks actually have to say, I'm done, please take the next one. But so if you wouldn't context switch, you could share the context by yielding, but we're not talking about that here. As seen before, the context is basically a set of registers and a stack, and the OS will decide who goes next, all right? So to do that, we need basically an OS stack and one stack for each task, and then maybe a heap or not. In our case, we don't have a heap, we don't do malloc or free in the Chromium EC firmware. Also useful to do that is somehow to have a time base. So on ARMv6 there is an optional systake, but most of the vendors actually implement it. If not, you can just use a normal timer. What it does, it gives you a periodic tick that will allow you to take an exception that then gets you into your OS. And you can use those events to run the scheduler to make changes on who runs. So how does Chromium EC do that? Well, so I picked, again, for this, the Cortex M0, because that seemed the simplest one to me from the different architectures they support. And, well, you have a struct task, which basically contains everything you need to know about the task. So there's a stack pointer, there's a bit mask of events, we'll talk about that in a second. And there's a pointer to the stack, which we can later use if we do some statistics to see the stack usage. We don't have a heap, we have fixed priorities, so at build time we know which task runs with which priority. We have different events like timers, mutexes, wake up events, peripherals, and we're using a 32 or 16-bit hardware timer instead of the systake, and that's going to be handy, which we'll see on the last slide how we can make use of that. All right, another picture to hopefully clarify things. The task states are basically either you're disabled, which means there's a global array, there's a task enabled at your index, there's a 0, so your task is disabled, it can't run. By writing a 1 there, this task gets enabled, so now it's ready. So how do I get out of the ready state into the running state? Well, that's easy. We're running always the highest priority first. So we get out of the ready state into the running state by being ready and being the task with the highest priority. So this FLS function gives you basically the first set bit in an integer. As we know at build time how many tasks we have, and they're usually not too many. They just use a uint32 and figure out which the first bit is, which is the task with the highest priority. All right? So from ready to running, be the highest priority task. Then how do we stop running? Well, there's two cases. Either we wait for an event, which could be a timer, which could be waiting for a mutex, which could be things like that. And all the events also have a timeout again. So I'll say task, wait for event, and then I end up in the state, wait for any event, and then I'll tell the scheduler, please do something so another task can run. The other case that could happen is wait for event mask, is where you say, I'm interested in those few events that I have in my mask that I passed the call, and then any of those would wake me up, and I get as a return value what happened. Yeah. So that would look like this in a very simple case. Say we have a high priority console task, we have a hooks task, which is basically a thing that deals with all kind of miscellaneous things in the Chromium EC. And we have an idle task. The idle task is always ready to run and runs whenever nothing else is ready to run. Usually the idle task is just something like a wait for interrupt, and the thing goes to sleep until we take an interrupt. The idle task wakes up, and that interrupt also set an event for another task, which then might get ready and then run. All right, let's look at this example. So we start out with the hooks task, which then enables all the other tasks. Remember, that's how tasks get enabled, is by writing to that array at that index. So first only the hooks task is okay to run, and then that one turns on all the others. Well, now the console task has a higher priority. Our scheduler kicks in, says, okay, now we're gonna run the console task, and that runs until it's waiting for an event, at which point the second highest priority task that's ready to run, which will be the hooks task, will start running. So then we go to that one also waits for an event, we go to idle, and so on and so on. All right, whenever an event happens, we call the scheduler to then figure out if something changed. If not, we keep running what we were running. Good, but back to code. How do we do that? In Chromium EC, there's a wrapper function for the supervisor call instruction that will create a exception. So what does an exception do again? Remember, it switches us to handler mode and it stacks some registers. So we looked at the calling convention before, right? So we know that parameters to function calls get passed in registers R0 to R3. So we have two parameters to this function, which takes a deschedule, which is a Boolean that says, okay, please deschedule myself after now I'm no longer ready to run. And the reschedule, which is like, please take this other task instead and make that run. And we pass those in those registers. We do a supervisor call, which then jumps into the handler, all right? In that handler, we push the link register and R3, that keeps our stack aligned, and we have the link register saved. And then we branch directly to a C function, because that's easier to write, okay? This C function is already our scheduling decision right there. So remember how we passed in register R0 and R1, the deschedule and the reschedule. Our decision is easy. So we remember the current task. If deschedule is set and we don't have any pending events for our task, we mark ourselves as no longer ready. Then we mark the reschedule task as ready. Then we find the next. Now another task is ready. Now we need to check again which task is the one with the highest priority. So that one goes into the next. Then we set the current task to next, and then we return what was the old one. All right? Remember, return values go into R0 and R1. So now we're back. We had only one return that was a uint32, so that will go into R0. We load the current task pointer into R3, we dereference it into R1, we compare R0, which was the return value of the function from before. If they're the same, we don't have to do anything, so we just return from our exception handler. So if they're not the same, means we need to context switch. That's when like a new task needs to run that wasn't running before. So we need to swap out the contexts before going back to our thread level. All right, that one is like the most complicated one. If you can follow that, then everything is easy. And so we get the process stack pointer into register R2. Then we move our current stack pointer. Remember, we're in handler mode, which will be the main stack pointer, into R3. Then we move R2, which is our process stack pointer, into the stack pointer. So we switch in handler mode what our stack pointer points to the stack pointer of the old task, the one that we're going to deschedule. Now we push R4 through R7 to remember them on the process stack of the old task. Now, as I said before, we're size limited because of the thumb instruction, so we can't directly access R8 through R11. So we need to copy R8 through 11 into R4 through R7, and then we push those also onto the old process stack. Okay? So now we're halfway done. We copy the stack pointer now into R2. We copy R3, which was our old, remember we remembered the main stack pointer into the stack pointer, so now our stack pointer is again the main stack pointer as normal for handler mode. Now we store into R2, which points to the old stack. We store into that the stack pointer of the old stack, and that works out because remember in a struct in C, your first element in a struct will have the same address as the struct, right? So we store the old task stack pointer into the old task description, and then we load from R1, which points to the next task. We load that stack pointer, and then we unstack all the registers back into, we unstack all those registers. Then we have to do the same for our 4, 5, 6, 7 because it's reverse order of what we did before. Then we put those also in the registers, and now we switch the context. Now all the registers look like they should for R3. So basically that's what we remembered last time R3 stopped to run. And yeah, then we just make that our process stack pointer. We return back to the handler, and there we're done. So we just pop our program counter, which was backed up. So now we're back in the next task. So that seemed pretty complicated, but like if you sit down with a piece of paper, I know this was probably really fast when I went through this. It's not all that complicated. So how do we get this thing started? Because initially we need at least one task to switch from. So the way they do is they have a scratch pad, which is just a 17 times 4 byte array, 4 because every register is 4 bytes. So we need 17 for one full context that we make that our R2, and then we move a 2 into R3 and so on. And then we go over those steps to finally call our scheduler, which then will detect there's a new task to run, and we switch to any of the other tasks. All right, task states again. We've seen that graphic before. So now we've figured out how we can switch contexts, but now we also need a way to actually make those changes, right? We need to be able to make a task ready. So how do we make a task ready? Well, we use a function called task set event. It takes a task ID and an event. So what we do is we have to look at two different cases, right? So either the thing that changes that task status originated in IRQ context, or it originated in task context. The task context is the easy one because we just atomically set the flag in the receiver task and then we call the scheduler. So that one is easy, that's the bottom one. It's like a mutex, for example. The more complicated one is the one where you originate in exception context. So the problem is, while you get one interrupt, you might get another one and so on, and every single time the priorities might change because each of those exceptions might unblock a different task. So you want to make sure to only call the scheduler when you're done with handling the interrupts. So there's a nice instruction to do that, which is PendSV, which is something like a software interrupt basically. And the way you make that work is you set the priority low enough so that all the other interrupts have a higher priority. So once you're done handling all the other interrupts, the PendSV will then get executed still in handler mode and call schedule. And that's how you set an event from interrupt context. There's a wait event, which is the opposite. When a task needs to wait for something, it takes a timeout. It must not be called in interrupt context. So the way it works is it arms a timer, which we'll see later how arming timers works. And then it basically goes and checks if my events are 0, then we deschedule ourselves. We tell deschedule by calling the scheduler with the deschedule flag set. We reschedule what's passed in with reschedule, and if the timer expires, then that would set a timeout event and would return, and if not, then the actual event would get returned eventually. And here you can see how you can use that wrapped up in a helper function. So basically, you have your timeout and you have your task that you want to reschedule, so that would be the idle task in that case. So if we go back, now we have basically a way to go from wait for events to ready, and we have a way from running to wait for an event. So now we're almost done, right? Another example for that would be implementing usleep, which just sleeps instead of busy waiting. It sleeps really and puts the task to sleep. The way it works is you read your hardware clock source, and then you wait for the events, and you remember all the events you get, and then you compare the event flag mask, whether there was a timer one in it, and if also you didn't have a timeout yet, meaning your time that you actuated is smaller than the timeout you were supposed to wait, you just keep doing that, and you order them together because they're flags, and you need to remember all the other events that also happened. Then in the end, you mask out the timer one because you don't really care about, and return all the other. All right, cool. So one thing I used and didn't talk about how it works is atomic operations. Well, the Cortex M0 doesn't have exclusive stores or loads, so all we can do really is disable interrupts while we do our thing, and that's basically how it works. So you disable the interrupts, you load whatever thing you want to modify, then you do your operation on that, you store it back, you turn on the interrupts again. All right, timers is the only thing that's really missing to make this whole thing work. The way this works on the Cortex on Chromium EC is they use one of the hardware timers that's microcontroller specific, so that's not a Cortex M0 level solution, but the microcontroller solution. Could be also a SysTick, but in that case, it's nice because they use a timer that also has a compare. Each task can use a timer via saying timer arm, you pass in a timestamp and your task ID. So basically, there's an array of deadlines, and every time there's an interrupt, we compare the time that we read from the timer with all the deadlines and see which ones are expired, and the expired ones, we can set the timer flag for those. And yeah, you can also cancel timers if you no longer need them. And yeah, that's basically it. All right, so that was super fast, and maybe I was faster than I should have been. Yeah, I have like half an hour left. Anyone, any questions so far? I bet this wasn't all super clear, or maybe I was wrong about things, so please shout if I said things wrong.
Is there any memory protection in between tasks?
You could. So for not Cortex M0s, but for an M4 or something, which they also support, you could use the MPU. So they have some targets for Chromium EC that use MPU, I think. At least I saw some configuration flags. Also, of course, if you have a microcontroller that has floating point, then whenever you task switch, you'd also have to take care of all the floating point state, which I on purpose left out because it would make it even longer and more complex. Yeah. Any other questions? Yes?
How many timers do you have typically?
In that case, there's a single timer, and then per task you can have one timer. So the way this works is you have basically an array with deadlines, and you always set the compare on your, as I said, the timer, the hardware timer has a normal counter that will overflow. If it's a 32-bit, for example, every time you have a 32-bit overflow, which happens if you run at whatever frequency, then say 65 milliseconds would be always your overflow. And then you also have the case where you want a shorter time duration, say a timeout of a couple of microseconds, then you always set your timer's compare unit to the closest deadline and use that one to trigger the process timers. And inside of that process timers function, you always set it to the next deadline. Or infinity, if there's no deadline, you set it to FFFFF, which will just wait for the full overflow. All right. Yes?
When you were setting up the start routine, did you not have to set up the cache, how you access data, registers and so on?
No. No, the Cortex M0 doesn't have cache, to my knowledge. The question was whether I have to set up cache. I just remembered I have to repeat them. Yes? Well, but you could do that if you know that doesn't happen. But so the question was if you could just tell your compiler to not use the extra registers. Well, I guess you could if I'm not a compiler person. I don't know, but yeah. Anyone else? Yes.
You compared this Chromium schedule to the FreeRTOS, for instance?
I looked a bit around. I mean, I basically picked that one. If you saw my talk from last year, I basically picked it because I thought there would be already working U-boot and kernel integration, which lets me, already talk to it, which turned out that at least the U-boot part was broken, so I had to fix that first. But I think FreeRTOS is more generic. This one was a good choice for me because it was basically meant to be used for what I needed. FreeRTOS has fancier mutexes to my understanding. For example, they do priority inheritance. The mutexes here don't. They're like you could create bad situations if you're not careful, but this one seems to be very well tailored to just being, board level control for fan control or LEDs or.
Have you seen that you can get the size down further on this one?
No, I hadn't compared because nice colors. Haven't compared. No. All right. So other stuff that I've been working on for that, I have my own little branch of OpenOCD that has thread awareness. It kind of works. It needs some cleanup before I can send out the patches. I wanted to look at porting it to RISC-V just because, and port to Microblaze because that might come in handy for another product. So yeah, questions on that? Is anyone interested in having thread visibility in OpenOCD? I don't know. Yes?
A bit more of a general question for you. So we've got a system which is running very bare to metal on a as an APR. And I've done lots of bare to metal stuff over the years, and I'm not quite clear when it's actually worth switching to a framework like this rather than do something. Do you have any feeling in general when you think, I'll stay there or I'll go?
So the question was, at what point does make an RTOS sense versus running bare metal, just having a while loop that goes through all the... All right. That's a bit a difficult one. It depends, on your complexity of the system, I would say. So if you're working all alone, you don't have colleagues and you don't share the work, for example, it gets easier if you have an RTOS because you can package out work packages between people. Power-wise, it might be definitely worth to use an RTOS because it's really easy to get the sleep right because you just basically have to make sure the idle task gets run at the right moment, as opposed to like from every possible state, make sure you go to sleep the correct way. I just personally found it easier to write code like that. I've done bare metal firmware that doesn't have task switching before. It makes it easier to reuse things. So there's pros and cons. Of course, you have a size overhead for having all this extra stacks. So if you're size constrained, for example, that might be something you want to consider. If you have a bigger system that has an MPU, that definitely would be worth considering an RTOS or even an MMU. I mean, so yeah, I would look at that. Yes?
Do you have any useful tools for estimating or calculating the stack size for different tasks?
They have some code in there that goes over the code, but I haven't looked at how they work exactly. But it's a valid point. You want to make sure your stack is large enough. Yes? Well, the idle task is literally one line of code in that case, and that's asm wait for interrupt. And then you go to sleep and wait for an interrupt, because that's the only thing that could make any other task run, right? A change in condition that triggers an exception. So that is not entirely true though, because the microcontroller might need to take a certain amount of time to go to sleep and wake up. So going to sleep might not actually be the right decision depending on how long you're going to wait in the idle task. So there's also a bit more clever way of doing that in Chromium EC, but I haven't investigated how exactly that works because my device is plugged into the wall, so I don't actually care that much about power. Yes?
Does that mean that when you go to the idle task, there is a lot more context switching going on? Or is there a quick way to go come out without doing the two extra context switches?
Between the idle task and...
So the idle task doesn't need a context,
in theory, yeah. You could probably take a shortcut there, yes. That's a good point. So the question was whether the idle task actually needs a context switch. You probably wouldn't because you're not using any registers in there. Yes?
What is the demand about the code size of Chromium EC? So if I do have to implement Chromium EC, my tasks with Chromium EC on Cortex M for like nowadays there are all these small good chips like the Nordic ones running on top of the Cortex M0 or M4, which do have a limited size of flash and memory. So how is the overload of this Chromium EC?
So the question was like how much overhead you have by using Chromium EC compared... Okay, so I can tell you for my case, the microcontroller I'm using has 128K flash and 16K SRAM. That's enough for 2 full copies of the firmware. You wouldn't have, I mean, Chromium EC is probably not a good call for just about any project. It's very good if you need this kind of board level control that does power sequencing, that does power button control, LEDs, fans, those kind of things, because that's what it was designed for, right? I mean, other RTOSs that like let you create tasks at runtime, for example, might be more generic than Chromium EC. That one just worked really well for my use case where I basically built a Franken Chromebook, but yes?
I've never heard of Chromium EC until now, and I'm still not sure exactly what it is. Could you maybe like say a few words about it? Okay,
so if you buy a Chromebook, they have a microcontroller on there, a Cortex M0, M4, or Nordic. There's a bunch of them, and it's the firmware that runs on there to do power sequencing, the thing that's on when everything else is off. So when you open your laptop to turn everything on again, those kind of things. And that's an It's open source. Google open sourced it, and yes.
How would you make sure that no low priority task would suffer starvation penalties?
How would I make sure that no low priority task, I didn't get the last part.
Suffer from starvation?
That is a very good point. I thought about that too. There's also the opposite case, where what happens if I end up in a while one in my high priority task. So the scheduler is definitely not smart enough to sort of keep track of runtimes of tasks and then say like, oh, that guy's running all the time, my low priority task is starving, or the opposite, where, yeah, that it doesn't do it. Yes? A tracer. I haven't looked at it. I mean, it's not like for safety critical things, right? It's for your laptop, sort of turning power on and off. So, you could certainly put in hooks that sort of trace events in there, but I mean, if your project becomes more safety critical, you'd probably want to look for one of the more established RTOSes where you get guarantees about things. I mean, it has basic output where it, like for event, can print events like an interrupt, print timestamps. So that's useful when doing board bring up or something. If a power supply rail doesn't come up or times out or takes too long, and you get sort of a list of when things happened, but nothing safety critical. All right. All right, anyone else? Okay. So with the systig is so basically I didn't write that code, right? I adapted it, so I used what they did because that worked. I thought about it, why they don't use the systig, and I think it's because they're doing this timer compare unit thing, where you would set the timer compare to the next deadline while you keep the timer running continuously. So that gives you basically like a continuous time base plus finer grain control over shorter deadlines in one thing. I mean, I made it run with the systig also because for testing purposes and to make sure I understand what's happening, I stripped out all the assembly files into a little project and just wrote a bunch of printf tasks that would run around. So you can definitely run it with the systig, but then you need to work around set it to the closest deadline thing. Unless you're okay with basically only getting it with complete systig cycle accuracy. So with the deadline thing, you can switch tasks faster and also have the long wraparound tick going. So yeah. Yes? There's more for the scheduler itself. I think does exactly the same thing. I think the stacking and unstacking would look different because you might have to take care of floating point registers or something like that. But yeah. All right. I think that's it. If there's no more questions. Thanks.